Yeah, so it's worthwhile to look at the PowerPoints. To be, I'm a little bit conflicted about telling you to look at the PowerPoints because the lead instructor has said, don't share the PowerPoints with the students. So, okay, and the reason for that is because it's a PowerPoint, you can edit it, right? And so so don't edit it. But the reason why I would share it with you is because it's got these links in it, right? So this is a video. One thing I don't do in class is I don't show other people's videos, right? I'm not going to show my videos because you can look at that anytime, right? And you can look at it in a way that suits you better. So we're not going to spend our class time looking at videos, but I do recommend, as a bit of a background, go ahead and look at those videos. And we've gone through all of this. So you see, there's a few videos there, right? So lots of background. The abacus explained. Here we got some other stuff about the loom. So there's lots of nice videos as background for the stuff that we've been talking about that you'll find as links. Those are all YouTube videos, right? So those are links to in the PowerPoint. And the other thing is, yeah, here we go. We just got some notes on Babbage's analytical engine. That's kind of worthwhile, right? Now, I am warning you on this because these things do show up in the quizzes and they show up in the exam. So it's worth your while to just, if you got a few minutes to go and just check these things, see what's there, and, just as a sort of a background. Now, I think we went through all of these. Look, there's so much in this lesson. I'm sorry about that. But I mean, this week we got a lot of sort of background. And as I said, it does show up in the quizzes. And there's a bit about Turing. There's a video about him. There's a video about the ENIAC. And this is about where we left off, right? A digital program. So John von Neumann famously sort of published a lot about this particular architecture, which we actually refer to as Von Neumann architecture, which allows a fetch, decode, execute cycle. Fetch being where we get one line of code at a time from a computer program, and then we decode that. When we decode it, it has to actually end up in a form which the computer can understand. Here's an assembler language form, which you might notice is kind of not like any computer program that you've ever written, but that's a sort of early version of computer programs, and it actually underlies the programs that you might write. If you write a program in C programming language or in Java or in Python, there could be you could get it converted to assembler language quite easily. And then for the computer to actually understand it, it must be converted to what we call machine language. And machine language is just zeros and ones. And that's a problem for us because we look at machine language and it doesn't mean much to us. But of course, this other stuff doesn't mean much to a computer unless it's got a compiler or an interpreter which interprets it for it. And of course, all computers do have compilers and interpreters. But there's a little more background on that in that video. And as I said, I'm not going to show you videos in class. You can look at videos in your own time. And yeah, look, lots more, right? So these videos here that you might look at are to do with these early mainframe computers. We call them mainframe. I don't know, the simplest definition of a mainframe, I guess, is a computer that fills up a room, I suppose you'd say, right? I mean, they're these large scale computers. I won't say that a mainframe is a particular power because nowadays we have powerful computers that are small. But yeah, generally, mainframes are more powerful than your smaller computers, and you find them in data centers, etc. But they are more powerful if they're up to date. But our smaller computers nowadays are quite powerful also. All right, we did not talk about this. And again, there's another video that you can watch about that. Dr. Grace Hooper. Can I make this a bit bigger? Yeah, I think I can. It's only 52%. So let's make that a bit bigger. So she became a rear admiral, which, as far as I know, is like the highest rank that you can have in the Navy, in the American Navy. And so she was busy writing actually writing the code to make a computer language. And so the computer language that she invented is called COBOL. You may have heard of it. COBOL was the standard business programming language from the 50s to the 80s. I actually learned how to write COBOL programs at university in 1987. So they're still using it then, right? All the banks are still using it. I bet there's still a lot of what they call legacy COBOL code out there. And actually, that was one of the COBOL programming language was one of the reasons that they had that what they called the Y2K event. The Y2K event, the problem with Y2K, you wouldn't remember that because you're probably born after year 2000, right? So there was all this worry during the 1990s. Oh, all our computers are going to die and crash when we hit to the 1st of January 2000. Why will they die and crash? The Y2K problem. The Y2K problem was that your dates in the 60s and 70s, there wasn't much memory on the computer. And so we use as small of numbers as we can for everything. And so for dates, they would just use 2 numbers, right? Like the year 1966 would just be 66. And and so for everybody's birthday and stuff like that, it'd just be put down as 66, 56, 86, whatever. So what happens when you get to the year 2000? See the problem? What is it? 56? Is it 1956 or is it 2056 or is it 18? So they thought the computers were all going to die and planes were going to fall out of the sky and all this kind of stuff. Of course, it didn't happen. But a lot of people made a lot of money, so they're trying to convert computer code during the 1990s so that they didn't die. When I say die, I'm talking about computer systems didn't die because of the Y2K event. That was a lot of fun. A lot of panic, which didn't really sort of cause too much problem. So yeah, who we got here? Jack Kilby and Robert Noyce, the invention of the integrated circuit or microchip. Integrated circuit on a microchip, and that's in the 1970s. And we do have this thing that's related to it called DRAM. And we got various versions of RAM, DRAM being one of them, dynamic random access chip. And so that's memory chips that you stick onto a little card that then is inserted into your computer. And so that all started in the 1970s. That was a good start. These numbers, you've probably seen these, right? Yeah, all right. So let's just spend a minute on them. A byte is 8 bits. A bit is represented as something that can be a 0 or a 1. A bit can only be a 0 or 1. You put them together to make a word, we'd call it. No, a word would be a couple of bytes. But a byte would be like 8 bits. And yeah, so we use a byte. A single byte could become a letter of the alphabet or a number. And so we actually have this code called the ASCII code. The ASCII code, we've got, because there's 8 bits in a byte, for each of those bits, we can have either a 0 or 1. And so the number of combinations that you can have of 8 bytes is 2 times 2 times 2 times 2 times 2, 8 times, or 2 to the 8. We're with me, right? 2 to the 8, if you did that calculation out, you'd find out that would be 256. So you can have 256 different combinations of 8 bits. And so there is a code called the ASCII code, which allows you to take one of those, any number between 1 and 250, between 0 and 255, and use that to represent a particular symbol. And so we have lowercase, uppercase, etc. There is an expanded code which allows for symbols which are not the Roman alphabet, because the ASCII code works for the Roman alphabet. You know what I mean by Roman alphabet: A, B, C, D, E, F, G. So there you can have an expanded ANSI code, which allows you to represent, for example, the Arabic alphabet. Anyways, that's done by a representation, picking out a particular byte. Anyway, so a byte is 8. If you got 1,000 bytes, that's called a kilobyte. And you've probably heard of that. 1,000,000 bytes is a megabyte. A gigabyte is a billion bytes. A terabyte would be a trillion. And a petabyte would be a quadrillion. And so that's quite a lot. Back in the 1980s, I was working for a telephone company in Australia. And one of the things that we did, we ran a big data center for when I say we, I worked for the information technology department in the telephone company. And one of the things that we did in the information technology department, so imagine we've got this little data center down here. So imagine a data center for a big phone company. It was the only phone company in Australia at the time. And yeah, so our computers, we used to sell space on the computer to the divisions of the telephone company. And so we would sell a terabyte of data space. All right, you can rent this space on our computer, a terabyte. That would cost thousands of dollars a month to rent. That was back in 1980. So I mean, the only place you could put a terabyte of data was on a mainframe computer, sort of a storage device. Now, what you can get that on your mobile phone. I saw it on the Samsung, S22 Ultra. One of the options was you could have a terabyte of data on a mobile phone. I mean, with a and so that's a solid state chip. So I mean, we've gone so far back. I mean, the power that we've got in our computers now is just amazing. The graphical user interface. I think I mentioned last lesson about not Bill Gates, Steve Jobs. He's quite an arty type guy. He was very smart, obviously, but he's a very arty type guy, and he wanted to make computers that people would want to be with in the first place. When I say be with, I mean, do things that not nerds would want to do. You know what I mean? So to draw things and, to have nice interface. And so he came up with a graphical user interface, and that kind of started where we are today. That came out of his idea. And of course, IBM had to copy it. And IBM had their own operating system one time, which was the OS/2 operating system, kind of short-lived. When I say their own operating system, because you'd know that IBM personal computers mostly run on the Windows operating systems. So Windows got a family of operating systems starting from back there. I mean, in the 1990s, they had Windows 3.1 was the first Windows that I saw. But before Windows, they had an operating system called MS-DOS. MS-DOS was like this, was a command line operating system without graphical user interface, no mouse, you're just typing stuff. And there's still an artifact of that. We're still stuck with that. Underneath the Windows operating system, they do have a sort of a DOS shell type thing, and you can go in and do DOS type commands, which are kind of like Unix commands, right? Now, so we're talking about operating systems. Just briefly, we'll move off this in a second. But the Linux operating system, you may be familiar with Linux and Unix. One of the things that's they sort of, I guess they sell themselves on, well, Linux has got a couple of good selling points. One is it's free. So it's what we call an open source operating system. So anybody can take it and download it and put it onto their systems, and they don't have to pay for it. It's perfectly free. The other thing is that it will run on just about any device. And so that's a big plus, right? It's not sort of built around the IBM architecture. It'll run on just about any device. So that's kind of a handy thing. Right, so here's some of those famous people. There's Steve Jobs, there's his buddy, Steve Wozniak. Steve Wozniak was the technical guru. Now, don't get me wrong, Steve Jobs knew his technology, right? He's a pretty smart guy, but the real sort of came from his buddy there. And same with now Bill Gates. Can't take anything away from him, like him or hate him. I don't know, his wife didn't like him anymore. He got divorced last year. Was it this year? Last year? Yeah. I'm not going to go into that. But his mate, Paul Allen, they worked together. Now, what I wanted to say about Bill Gates is when he was like 13 years old, his father, I think, worked at University of Washington, which is in Seattle, and they had one of the best sort of computer labs of any of the universities in the United States at that time. And Bill Gates, 13-year-old, used to go up to the University of Washington as a 13-year-old kid and sort of write computer programs. So, I mean, the reason why I'm going to mention that is the next thing is Bill Gates, as far as I know, does not have a university degree. Okay, he spent 2 years at Harvard University studying computing. And, he had an opportunity that came up that he could provide an operating system for the soon to be released IBM personal computers. And he said, hey, let's go make money. And him and his partner, Paul Allen said to do that. Why do we need a degree? We're just going to be business people. And yeah, at one point, Bill Gates was the richest man in the world. And so that worked out pretty well for him. But the point that I wanted to make, yeah, he didn't finish a university degree, but he knew a lot about computing. You know what I'm saying? I mean, he started doing computing. He wrote a little program when he was like 14 years old or 13 years old that he gave to the Seattle Police Department, which for them to manage their traffic lights. so, so I mean, he knew what he was doing. So here's some other sort of breakthroughs in technology. We got the mouse, which started off by Stanford. I don't know if you know about Stanford. Stanford's a university in, I think it's in San Jose, but that's in just in the greater San Francisco area. And you may know that like San Francisco is the most expensive city in the United States. And so why is that? Down the San Jose Valley, all of these companies are there, like Hewlett Packard. Now I won't say Microsoft because Microsoft is up there in Seattle, but Google, the companies we're familiar with, they're there, and they bring people in, and these people are, young people like you who some of them have degrees and some of them don't, but they are excellent in writing computer programs, and they're all getting paid $150,000, $200,000, $300,000, $400,000 a year. So they got big salaries, and so that's really pushed up the prices there. Now, why do I mention Stanford? Because Stanford is a university there where some of these things started off. Stanford is a university that does business startups. A lot of people go to university in Stanford. Some of them don't ever finish their degree. They just go there for a couple of years. And because what's happening in Stanford University is investors, people with a lot of money, they'll go to Stanford, they'll meet these smart students that have ideas, and they'll say, okay, let's start a company. And that's what they do. They'll go away and start a company. You may have heard of Theranos. Elizabeth Holmes, who's in jail now. She started a company called Theranos. She did 2 years at Stanford University, met a lot of rich people. She was a billionaire for a few months, few years, until they figured out that her system didn't actually work. Yeah. So she's going to jail because for fraud. Yeah, because the people who lent her a lot of money, when they figured out that the system didn't work, they said, "Oh, you lied. You can't do that." All right, so we've got some other things here. Yeah, the start of the internet. You could say the basics of the internet started a long time ago with ARPANET from the Department of Defense. And what was the deal with ARPANET was that they made a communication that they could use between people in universities. It just started out with Salt Lake and San Francisco, I think, and then it went to a few other universities. But this is back in the 60s, 70s. So yeah, there we go, 60s, and in MIT. So they were emailing each other, right, over this little network that they had, and that was the basis of the technologies that now give us the internet that we all know and love. And there's a lot of background there on that if you get interested. Bill Gates saying how much? Okay, did he say that? 650? Yeah, I don't know. Obviously, he wouldn't say that now. Other guys in the news. I don't know if you know this guy, Sergey Brin. So they're at Stanford University, and what did they start? I think Google. Yeah, these are the Google guys. So Sergey Brin's been in the news this week. Why? He's getting a divorce from his wife. Why is he getting a divorce from his wife? Because he said that Elon Musk had a short affair with his wife. And so I checked that out. And so just because you're rich and you got lots of technology, it doesn't mean you're happy, right? He's not very happy at the moment. He's not very happy with Elon Musk, who used to be like his best friend. Not his best friend anymore, right? And his wife's not his best friend either. Turns out. All right, so that's kind of interesting and fun. Okay, so Google is these guys came up with this word. Google comes from Google, which is a 1 followed by 100 zeros. In other words, big, right? So the idea is that we got a search tool that you can use to sort of index all the information in the whole world. Well, actually, it'll just index all the web pages in the whole world, right? And so every web page gets indexed. And so you can find stuff by just doing a search. And of course, there's lots of other tweaks that you can do to those searches so that you get things that are more like what you hope the person would have. And there's a little bit of history. 2010, we got the iPad, right? And you would know that we're sort of on the territory now where we're going to get into the Internet of Things and all that kind of stuff, I suppose. It's just going to be a, no, that's not what I want. So it'll be this one. I want to use the PowerPoint. I like the PowerPoint because use the PowerPoint, then I can show you the notes. So all of these are familiar to you, right? I think it's a pretty big breakthrough in the last 15 years. Is it 15 years? The screen technology. And that breakthrough is going further, right? So now I've seen people with the Samsung phones that fold. Okay, so what we got is a screen which can bend. And so, I mean, some people say the next place is going to go is you'll have something you can wrap around your arm or something, so that your device doesn't have to be the form factor that it is now. So we've got all of these devices. Some of you are wearing smartwatches. I have one. It's not as fancy as the ones you're wearing, I suppose, but mine is from Garmin. It's a sort of a GPS tracking company. And so we use it for like if you're in a race and you're doing laps, it'll time your laps for you perfectly. It measures your heartbeat, all the rest of the stuff, everywhere you've been. Everybody's got that now, right? So this idea of the, you know, I should move this so you can see that. What is a computer? I think this is trying to show all the computers that we have in our house. Yeah. Controlling your air conditioner, lots of other things. And this would move us towards the idea of the Internet of Things, where you can have a small device which just has an IP address which connects to your internet. And you can control things from, so you could be sitting in your office at home and you could just go onto your mobile phone and say, all right, I want to turn up the AC. I want to, you know, see what's in the fridge. You know, I want to, you know, I want to see what's on the baby camera. And yeah. Okay, so here's some wearable technologies. As I mentioned, the phone, and there's some other devices there. Smart fingers. So one of the things about the wearable technologies is you have to have some communication between the device and something else. So for example, this one I've got a sensor in there that measures heartbeats. And so that's good to see how much exercise I've done or whatever. But so what could we do with that? Well, it's just on your phone, on your watch, or some other little sensor. That doesn't help much. You need to communicate somehow. So most of them use a Bluetooth, or it could be a Wi-Fi connection, but most of them use a Bluetooth to another device, like a mobile phone, which is really quite powerful. This actually can sort of save lives, they say. So we talk about what we call a personal area network, where you could have various sensors on the body of a person, and then you could have some application on your phone which connects to your doctor. All right. So if you're a person that has a heart problem or something like that, and your heart starts to perform outside the normal parameters, you know, that a message could go to your doctor, right? And then your doctor could sort of intervene. You could talk to them in a Zoom call or something like that, and they could sort of suggest some medicine that you might have, or they might have somebody come out, and that might save your life, which is, you know, saving lives. That's usually people like that. Smart TVs. Yeah, when I bought a new TV, my daughter insisted that it be a smart TV, right? So that she could control it with her mobile phone, right? And so that, you know, you could have all your Netflix and your Amazon Prime and all of that, the rest of it. So most of us got smart TVs now, I suppose, if we bought one in the last 5 years, unless you're still holding on to some of that older technology. Now, what about these things? These are actually computers, right? So this would be some kind of data communication or data storage computer. The network printer is here. Yeah, we use network printer. So we don't, if you went to the teachers' offices, you'd find that teachers' offices don't have printers in them. We all use the same printer. So that's a network printer. So we print over the network. And, you know, the operating system handles that quite well. And this is some kind of server. And as I said, there's lots of explanation down there. Okay, so we have these huge server farms. Lots of computers together, and they might be networked. So we do a lot of things. We say we're working in the cloud. So working in the cloud, you can put your whole business onto the cloud. Very great benefit to businesses. So what I mean by that is, what if you wanted to set up a new business and you had this plan that it's going to be quite a big thing? You're going to need a lot of computer power. So you go and build yourself a data center. You know, I mean, this is going to cost you millions of dollars. All right. The other thing you might do is you say, oh, I'll go to AWS, which is an Amazon company, or I'll go to Google, and they have server farms in Iceland and in Ireland, and I will sign a contract with them. We'll upload my whole business onto their server, and it's just in the cloud. And so then instead of me building a whole lot of computer infrastructure in my hometown, I will pay them a monthly amount. I'll pay them a monthly amount, and all my stuff is on there, and they've got it all secured and all the rest of it. Now that's really good, we say, for scaling a business, scaling up and down a business. So if you have a few customers, you know, you don't have to pay too much, right? You pay a small amount a month. And as you get bigger customers, you just pay a little bit more. And, you know, you don't have to go buying more computers and stuff. And if you go out of business, which happens, you just cancel a contract with Amazon, AWS, and you don't have to pay next month, as opposed to building the big computer center here, and then you go out of business, and now I got to sell all those computers. You know, you're going to have a big loss. And so, yeah, so that's very attractive to most people. And most of us are doing stuff in the cloud, right? I mean, so the notes that I've got that I'm showing you here, they're stored in the cloud, attached to my one, which is, I don't know. Yeah, OneDrive, which is in the cloud. It's not even here in Qatar, right? And it's pretty quick. And so the good thing about that is, yeah, I go on holiday to Europe or something like that. I want to see what I've done in my class. There's my notes, right? And I can pull them up on my phone. Mind you, they're kind of hard to see because it's going to be small. But you know, I mean, all of those, all of the stuff that you've been using, it's very good for personal things as well, right? You put all your personal stuff on there. You don't have to worry about hard drives, stuff like that. It's just in the cloud. I guess what you have to worry about is you have to keep your account up to date. You know, don't miss the yearly payment. Okay, so there's some other things about computers. What is a computer? There are lots of different things. They store data, they do computations, they're quite versatile. I think the graph here is, yeah, it is Moore's law. I should make that a bit bigger so you can see it. But the point is, this is a logarithmic graph. I don't know if you know what I mean by logarithmic graph, but instead of each square being increasing by 1 or 10, it increases by 10 times as much as the one below it, right? So each step up is 10 times as much as the one below. And so if this was a normal graph, it would be kind of like going straight up. But because it's a logarithmic graph, we got a gently sloping line. But basically, this could represent the power that you get for the in the size and in the cost. And that's Moore's law, is that the developments have been that things get a lot smaller and they get a lot more powerful and they get a lot more cheap. And that's definitely still continuing. So at the bottom of the scale, probably got a year or something. Yeah, there's the same thing there. So again, logarithmic scale. And what we see is the performance versus the dates. So as the time has gone up, the performance, it looks like a straight line, but actually if we had it on a non-logarithmic scale, it would look like it was going straight up. So our performance is just going up so much. The idea here that we're trying to represent is the artificial intelligence, which some of you might want to do, the AI or course that we have. And so here we had a situation back in 1997 where a computer beat a world famous chess player. So far with artificial intelligence, they've been quite good in a very narrow specific field. So you can get a program, you can set up a computer that'll beat somebody in chess. But that's a narrow area, right? With human intelligence, if we're trying to get a computer that represents human intelligence is quite varied. We're very flexible, right? What we do with our minds, you know, some people never played chess, but they're still intelligent. They do other stuff, right? And so can you get a computer to handle all that wide variety of intelligence that people have? That hasn't happened yet, I don't think. But we do have artificial intelligence in narrow areas. And what we can do is we can gather a lot of data in huge data sets, and then we can train a neural network to see particular patterns in the data, and then based on those patterns in the data to come up with some decisions. And there's other people here at the college that know a lot more about that than I do. And you'll run into them if you want to sort of study artificial intelligence. Further, same idea. Computers are beating people in various games. You may have heard of, in a previous lesson, we talked about Alan Turing. So they have the Alan Turing test, right? And the Alan Turing test is basically, we will say that we have arrived at artificial intelligence if an expert can contend with a computer, and it's not without seeing it, it is not able to differentiate the computer from a human. In other words, the human expert is playing against a computer, and they don't know they're playing against a computer. They think it's another person. Then you've got artificial intelligence, apparently. Again, more sort of advances in computing. No, I think I answered that. Has artificial intelligence become smarter than humans? No, I don't think so. But will it? Maybe. You don't think it'll ever become? Okay, so some people say that the people who are best, who predict the future before the scientists are not the people that predict the future. Some people say, well, they will, but who's ahead of the scientists in predicting futures are the artists, some people say. And so the artists have been talking about this for a while. You might have seen the movie called The Terminator, Starlink. And the idea there was when the computer eventually reached sort of self-awareness and Starlink, and then that became the end of the humans, because when the computer reaches self-awareness, they'll realize, well, you know, these humans, they're not doing a real good job. It'll be better for us robots if we didn't have those pesky humans around sort of messing up the place. So let's get rid of them, you know, and why wouldn't a computer do that? Anyway, so The Terminator is a movie that came out in like 1980 something, right? So as I say, the artists are way ahead of the scientists, you know, and thinking about this. The scientists are saying, well, yeah, that might happen, but, you know, not yet by a long way. That was, I think that's enough on that. We do have a little exercise, and that'll bring us to the end of today's lesson, I think. Yeah, how are you guys going? We've been here for only a little over a half hour. So last thing is critical thinking. There we go, because I gave you the assignment and most of you have done the assignment. So let's look at some critical thinking. What are we gonna do tomorrow? If we do we have a class tomorrow? This is the end of the week, right? Oh, so we got to do this now. All right. So if you were exposed to, when you're in high school or in junior school or whatever, if you're exposed to a lot of sort of word problems, then this will seem familiar to you. If not, it's probably worthwhile. But yeah, it definitely helps you with your flexibility of your mind. Can you see the pattern? Yeah. Maybe you could even represent that pattern mathematically. I think you could. So what's going to be here?
5 boxes high and 5 boxes wide.
Yes, if you include the corner box. Yeah. So on top of the corner box, there'll be 4, and then going out, there'll be 4. And then here, if you put the corner box down there, you'll get 5 and 5, right? So what I think you could see is that we've got whatever this number is, we got 2 of them, right? So this is number 3. So we got 2 lots of 3 plus 1. And here we got 2 lots of 2 plus 1. And here we got 2 lots of 1 plus 1. So you could write a mathematical formula for that, right? Y is equal to 2x plus 1. And you may have seen something like that, where y is the number of blocks, right? That would, now, if you could do that, you're ready to, because anything that you can put in a mathematical formula, you can put that into a computer. The computer will handle that very nicely. All of our programming languages will do that. So you might write a Python program to do that. And why would you do that, right? Well, maybe you had to do this like 2 million times. Maybe you wanted to answer the question, well, what if I went out here 2 million times? You know, how many of these would I have? Well, you could very easily solve that using a computer. Actually, that's a very trivial problem, but yeah. Here's one that is, here's one that's kind of really, I would say quintessentially computer programming, or it's identified with computer programming. You will come across this problem, or this problem is useful to you as a computer programmer. Now, why I say that is because this problem is part of our sorting. If we think about how we're going to sort things, this problem will help us. So the problem is we got 8 marbles. That's sorting and searching. Sorting and searching, right? This would help us for searching. We want to find one of those marbles is lighter than the other marbles. And only one of them is lighter, but we got 8. What's the least number of steps we could use to find the small or the lightest marble? And when I say small, no, they're all the same size. We can't tell them apart by their size or their shape or their color. The only way we can tell them apart is to weigh them. Now, of course, we could go in there and weigh each one. And then we would find the lightest one. But that would take you 8 operations, right? So that's, you know, couldn't we do it faster than that? All right, so the trick that computer people use, and they use this trick all the time, there's actually an algorithm for it, is we're going to do a binary search. Binary search. Okay, binary, you know what that means, right? Binary means it can be either one or the other. So what you do is you take your 8 marbles, you divide them into two lots. These 4 marbles there, those 4 marbles there. We'll weigh them and see which one is heavier. The ones that's heavier, discard it. So that's 4 marbles that you don't have to measure, because we know we're looking for the lightest one. So the lightest one must be in with these other 3 marbles that are lighter, right? Then take these 4 marbles, because you discarded those 4, take these 4 marbles and break them into 2 lots. What 2 lots of 2, and discard the heavy ones. Now you only got 2 marbles. Weigh them, and one's lighter. Takes you 3 measurements instead of 8 measurements. Binary search. The other one would just be the search where we just measured each marble. That would be a very inefficient search. We'd call that a serial search, right? Going through one at a time. I remember reading a fellow was, he posted something, it was like on a blog, and he said that, you know, he was given a bunch of, him and a bunch of people in a lecture theater were given like, I don't know, 100 sort of things to sort. And everybody else was going through one at a time, and he did a binary search. And it was slower for him at the start, but at the end. Yeah. Okay, so we got something else there. Number tricks. Oh yeah, this one's tricky. It is. It's tricks. Do I have a pen? Yeah. Okay. So the number tricks thing. So what can we do there? We've got to we need to use all of these numbers, but use all of those numbers only once. And then from that, we're going to get this number, and this number. So you can add them together. You can divide them, subtract them, you know, any of those basic operations you can do. And from that, you have to get this number. So what combination of 3, 4, 6, and 8 is going to give you a 4? Okay, you probably have to think about it a bit. To be fair, I had to think about it a bit. I got a few here. So, I mean, what you could do, well, look, if you took 6 times 8, that's 48, right? And you took 3 times 4, that's 12. And you divided 48 by 12, you get 4. There's lots of other ways you could do it, right? So this is just sort of critical thinking. And should I go through all those, or you like to have fun doing it yourselves? No? Oh, let's have a look at what else we could do. Yeah, so we could get, again, I have to, if I even got it. Oh, I missed these on the first page. I missed some. The peanut problem. Should we go back and look at that? All right, let's do this first. So another one that you could do, let's say you want to get the number 14. How would you get 14 out of that? So what you would find is that 6 plus 4 that's equal to 10, right? And then 3 times 8, that's equal to 24. And 24 minus 10, that's equal to 14. So that's one you could do. And as I said, I wish this just came to my mind automatically. I had to actually look at it a bit. So I don't really have time today unless I sort of tease you a bit to go through all those with you, to let you go through them, but you could if you wanted to. Now, what's the other one? So that's the number 4 and the number 14. How are we going to get the number 10? So how we get the number 10? I think we do this. 4 plus 8, that's equal to 12. Minus 6 divided by 3, that's equal to 2. So that'll give us 10. So I mean, there's, as I said, you could go and play with that a bit. Another one we've got is this peanut problem. Why did I miss the peanut problem? I sort of went through that too quickly. There it is there. What do we know is we've got 81 peanuts, 81 nuts. Okay, and the nuts are made up of almonds and Brazil nuts and cashews and peanuts. So the total of all the nuts is 81. And then we know that what? There's twice as many Brazil nuts. So Brazil nuts is equal to 2 times the number of cashews. And peanuts is equal to Brazil nuts. And almonds are what? They both, twice, that can't be right. Yeah. So Brazil, twice as many peanuts as Brazil nuts. Is that right? So Brazil nuts is equal to 2p. Is that right? Twice as many Brazil nuts as cashews. Yeah, wait a minute. So no, this is C, peanuts. Peanuts is equal to 2 times the number of Brazil nuts. Okay, and then, so we got B, then A is equal to B. All right, so then you can just sort of, you could do it by replacement. You could say, well, A is equal to B, right? And you could say P is equal to 2B, right? And then you could say that C, 1C, sorry, 1B is equal to 2 C's. So 1C would be a half a B. Then you could add those all up and you get 1, 2, 3, 4 and a half. So 81 is equal to 4.5 times B. So if you divided 81 by 4.5, you'd get 18. So there's 18 Brazil nuts. So 81 is going to be equal to 18 Brazil nuts plus, so, and actually almonds is equal to Brazil nuts, right? So 18 is 18 almonds, 18 Brazil nuts, half the number of Brazil nuts for cashews. So that's 9 cashews and twice the number of Brazil nuts for peanuts, so 36. Add that up and it should be 81. Anyway, so as I say, it's just kind of a little bit of fun. I'm not sort of asking you to do that because I'm kind of rushing us through, but you see how you do it, right? As you see me do it, you're like, I'm hoping and I'm thinking that you're saying, oh yeah, I could do that. Yeah, given a few minutes, you'd do it, right? Am I right? You would, yeah. Or you'd wait for me to do it. You would do it, right? So logic. So the logic problem that you've got there at the bottom of that page is the basic logic is, is this true false thing, right? It can be this or it can't be that. And so we've got these people, we've got Ahmed, and we've got Badr, and we've got Miriam, and we've got Fatma with a P, H. And it's important that they changed it to a PH instead of a F, because we have some rules there. The rule is that the person has a favorite subject, but the favorite subject cannot start with the same letter of the alphabet as their name. And so that means that Fatma her favorite subject could not be PE, because PE starts with P and her name starts with P. All right, so she can't be PE. And so there's some other things that we need to know. So let's go through the list.
go through the list. Butter and the person with the, well, that doesn't really help us too much. Fatma and Sammy both dislike this experiments. So their favorite subject's not going to be science. All right, so which one of these subjects is science, right? Okay, well, biology is science. So Fatma and Sammy, they're not going to be biology, they're not going to be biology because they don't like experiments. Miriam is very talented, is on the track volleyball. There you go. There's our first real clue that's going to identify one person, right? Miriam likes volleyball and track. So that's going to be PE, and that P is good because Miriam doesn't start with a P. So we can say that, we're going to just say that Miriam likes PE. So now by process of elimination, nobody else can like PE. There's only one favorite subject per person here. So Miriam's done. She's a PE person. Sammy jokingly says that I can't draw a straight line with a ruler. That probably means he's not going to be an art type, right? Do art people need to draw straight lines? So probably Sammy doesn't like art. And okay, so now we can go back. This one doesn't really help us. Butter and the person. Oh, well, it does in a way, yeah. The social studies guy, what it tells us is that Butter cannot like social studies because he sits with the social studies person. You can only be one person, right? You can't be the person to sit with. So Butter doesn't like social studies. That's somebody else. All right. So what else? Fatma and Sammy both dislike experiments. So they don't like biology. So that might help us, right? Okay. So Fatma, she can't be PE, and she doesn't like biology. So, well, PE, she can't be PE because that's already done, and because of the PE. But what about Sammy? He doesn't like art and he doesn't like biology. So what's left? We got. Could Sammy be a math? It can't be PE. So physical education's gone. Biology they can't be. They could be social studies or art. Well, Sammy can't be social studies because it starts with an S. Oh, he's probably not going to be art because he can't draw a straight line. So maybe he would be math. Sammy would be math. I think that might work. So Sammy could be math. So that's one less. So now we're down to social studies and biology. Sorry? Who's going to be the biology student? Well, it can't be Butter. It can't be Fatma. It can't be Sammy. So there we go. Yeah, it must be Ahmed, right? There's biology. That's good. So we're getting those down. So we're down to art and social studies. Sammy's gone. So Sammy's gone. Ahmed's gone.
Mariam.
Sorry? Miriam could be what? Oh, well, she's already PE student. She likes PE. So what? So Fatma, could she like social studies?
Yeah.
Yes. So that would work. And then Butter sits with him, and he's got the last subject, whatever it is.
Art.
Does it fit?
Can this be vice versa for Butter and Fatma? Can Fatma also like art and Butter for social studies?
Could Fatma like? Quite possible, I guess. I'm trying to think about it. Could Fatma like art? What is there any reason she couldn't like art? Yeah, I think you could probably just swap them around.
But sir, you put an F for social studies near Butter.
Oh yes.
Yeah. So, oh yeah, so that's why. Yep. So Butter can't be social studies. So very good. So the logic works. There's only one answer. Very good. Thank you for that you were able to see that. And this one we did all the numbers. The last one, triangular sums. I'll give you a clue. There's two numbers you need to add them up to. It can be either 67 or 68. Look at the corners. The corners should be either all even numbers or all odd numbers. If you go with the even numbered corners, then you're going to get your 67 number. If you go with the odd number corners, you're gonna get your 68 number. So there's a big clue. I'll let you figure out the rest of it. Does that sound good? You want to do it now? Huh?
We don't know.
Do it now. Okay, yeah, let's not mess around. All right, so the numbers are 20, 22, and 24. So like I said, do the even numbers for the corners, and then all the numbers have to add up to, I think, 67. So so we've used this number, and this number. We've got 21, 23, and 25. 20 and 24 and 20, that's 44. To add up to 67, we put a 23 there, right? And then 20 plus 22 is 44, 42. Then we need a 25 there, right? Okay, and then the last one, 24 and 22 is 66, 21. So it works. Do the corners. And that, if we wanted to get to 68, we'd do the opposite. So we'd say, all right, well, let's take the corners and go 21, 23, 25. Now we want to get to 68. So 46, 22, right? That's going to get to 68. 21 and 44, 24. That'll get to 68. 23 and 20. Is that right? That's already 48, so that must be a 20. Works? Isn't that fun? I guess the benefit of that is to see the pattern, right? Evens, odds, either go in the corner. So it's like we got two different triangles, right? We got the outside triangle and we got the inside triangle, and they swap. They're either evens or odds. You'll see a lot of stuff like that in computing and sort of problem solving generally. So we solved all those problems. Wasn't that fun? All right.